Oh, oh man, it's so long. Oh well. Uh, we resume the laser printer repair project that never ends. Alright, quick connect fitting. We're going to use that to bring the 24 volts off the printer over by us. Huh. Okay, so the two yellow lines are just signal lines. They're 24 volts too. But we want the 24 volts. That's permanently on. Okay. We've got to run that all the way over to me. So we need like 14 inches of wire. I guess this is kind of long. I could probably work with this. Okay. Alright. Huh. Well, shoot. This is really not the right one, though. This one. Okay, so we're gonna not do the quick connect method. This is something we can plug into directly. Okay. We'll need a red. We will need a quick connect, actually. Here we go. Okay. Okay. Now from this, we can build off of that. Uh-oh. Alright, so now we need a male coming off this. Okay. Okay. Now we've got it to here. Um... I need a black female. And a red female. Okay. And then I need a red male. It's not quite red, but it's close enough. Alright. This is 24 volts live. They cannot touch. They're live. Alright. What's next? Use white quick connect fitting to clip 24 volt power and ground lines coming from laser printer and run wire from that quick connect over to me, and then attach another quick connect, and then attach that to jumper wires. Stick 24 jumper wires and a breadboard. Okay, we completed both of those. Very nice. Span between the 24 volt positive and ground with a 10 UF electrolytic. Run the 24 volt positive into the left pin of the 7805 regulator. Here's the electrolytic. Let's get that going first. Oof. He's got too much solder on him. I think I'll use electronic side cutter to trim the little solder ball off his legs. Beautiful. Oh my gosh. Oh my gosh. That scared the hell out of me. What? What? What just happened? My hands are shaking. What's going on? What actually happened? I mean, a capacitor can span between positive and ground. And I had the stripe side toward black, unless if I had black and red mixed up, which is possible, I guess. It's a possibility. Maybe I had black and red mixed up. I just had an explosion. What? Is this normal? This is why you always want to work with electronics while they're live. That way, any wiring mistake gets revealed to you very quickly, rather than putting together a complex circuit and finding out later something's going to blow up and not knowing what it is. I knew right away something was wrong. Because everything's live. This is still live. Everything's still very live. I haven't unplugged in anything. There's all this weird hairy stuff that came out of that electrolytic capacitor. I I can't wait to find out with my multimeter what's the if we have the polarity right on these wires, red and black. If the polarity's wrong, we just learned something. We learned if you plug in a multimeter or an electrolytic capacitor with the stripe facing the wrong polarity, it causes a short-circuiting effect. That's crazy, man. It freaking blew up. There's nothing left of it. I don't even know where the cap went. It's an aluminum cap on an electrolytic capacitor. It's gone. That was like a firecracker. That's weird. Did I break my printer though? Dang, my printer's a beast. My printer's like, I didn't even feel that, bro. We're good. We're good. I don't mind blowing up the occasional capacitor. I got this. I'm a high power supply. That's my bread and butter. Well, sweet, man. I don't know. I could have broke my printer right there. $24 volts. Alright, my polarities and everything were correct. So that leaves me only one idea of why that might have happened. Which is, that capacitor must have been not rated for 24 volts. If it's not rated for 24 volts, I guess the proximity of the various plates of the capacitor, which are little aluminum plates rolled up into a tube, would be enough for the 24 volts to cross over from one plate to the next. That's how a capacitor works. It's metal sheets rolled very close together with a tiny gap, and if the voltage is too high, it will cross that gap, creating a short-circuiting effect, which is what you saw there, which is why the capacitor blew up. It had nothing to do with my polarity being wrong or anything like that. So I'm glad for that learning experience. We learned that, wow, you do not want to use the wrong... Well, let's look at what it looks like. I want to use the wrong rating on a capacitor. I knew I needed a 10 UF electrolytic. I didn't even consider the voltage though. I just picked a 10 UF one. Alright guys, I'm about to show you this is what happens if electrolytic capacitor is plugged in. It blows up. This is what it looks like blown up. That is absolutely incredible. Wow. So that's the little plates of it that are rolled up normally with little hair in between spanning them. And I guess if the voltage is too high, those hairs aren't enough, and these little plates, yeah, see? A little electric plate onto a little leg. That's all a capacitor is. Wow. That's pretty cool to actually see it taken apart. It's almost like a blessing that happened. There it is. They just put hair in between a metal sheet. How very cool, man. Here's the other one. One's positive, one's negative, or whatever. This doesn't mean I'm not the world's greatest roboticist. Not checking a label carefully enough doesn't mean anything negative about me. I never even consider that 24 volts wouldn't be compatible with, you know, your typical 10UF capacitor. I just assume most capacitors are at least, if they're 10UF, they're at least, I don't know, 60 volts, 100 volts compatible. So that was very odd. But hey, we cleaned up the mess. Lost one free capacitor I got off of one of my circuit boards. I've got a million more. No big deal. We're still in control, guys. We have not lost control here. Alright, let me do a multimeter test again here. I don't know why, I don't know, I'm feeling paranoid now. I can't trust anything anymore for a while. I just want to measure these voltage rails, make sure I understand breadboards. I feel like everything's in question now, because I still am like kind of weirded out by what just happened. We have the positive and ground 24 volts coming directly from the power supply of the printer here. And I just want to measure it to make sure we're getting the expected readings on the expected tracks. "24 volts positive." Okay, so everything is as we want. It's all looking right. What a weird thing that just happened, you know? The striped side goes toward black. I had the striped side toward black 100%. So I'm telling you, that thing must have been rated for like 5 volts or something weird. Which is why it blew up. I guess that's not the first time something blew up for me. And I'm guessing it won't be the last. So you never know when there's going to be some big surprise. When Larry does electronics. But hey, part of that all comes down to me working live. I like it all plugged in. Everything's live when I touch electronics. I don't shut off the breaker. Where's the fun in that? I learn with real-time feedback because everything's running all the time when I work on electronics. That caught me very much off guard. I guess it woke me up. I'm not sleepy anymore, so there's a win. Shoot, my hands are still shaking. I had a you know, when you light up a firecracker and it explodes, it's like, okay, that was exciting, I guess. But when you don't light off a firecracker and it explodes, that scares the hell out of you. Especially if you're just quietly working in your office. It's just, you're not expecting a loud explosion. It's just like, whoa. That was terrifying. Okay. Next thing we need to do is get a replacement electrolytic capacitor, since our last one has exploded everywhere. Holy cow. Or not. Let's not even use one. Heck with it. It's not meant to be. We don't need one. Span between the 24 volt positive and ground with a 10 UF electrolytic capacitor. Okay, so that's out. The whole point of that is just to smooth out the 7805 regulator, but you don't actually need it, I don't think. Run the 24 volt positive into the left pin of the 7805 regulator. .24 volt positive into the left pin. Run the negative into the center pin. Alright, let me unplug the negative for now. No, I want to pull it out. Alright, 24 volt positive into the left pin of the regulator. And put the ground pin into the center pin. Gosh, I feel like a bomb squad now. I shouldn't say bomb when I'm working on electronics that look like bombs, but still, I mean, it was a bomb. It blew up on me, didn't it? No, I shouldn't even say that. It was not a bomb, it was a part that short-circuited. I gotta watch my words. Alright, This project looks too bombish to say the bomb word. Everybody thinks of bomb whenever they see any electronics. It's ridiculous. Okay. That's another win for us. Run the 24-volt positive into the left pin of the 7805 regulator and run the negative into the center pin of the 7805 regulator. Done. Get wrecked. Now connect the 5-volt red line to the center pin of our MOSFET. Okay. Okay. Connect the 5-volt red to the center pin of our MOSFET. Connect the right pin of our MOSFET to the motor. Connect the ground of the Attiny to the... What the heck? Oh, connect the 5-volt red line to the center pin of our MOSFET. Okay. Let me make sure it is 5 volts, right? Try to get a red line. I'm going to run a test real quick. I want to verify that we got 5 volts coming out of this bad boy. So I need to tap the ground and the 5-volt line to make sure. I'll use my mouse as a backdrop for this. Okay. Okay. I need to touch the ground somewhere. Oh, come on. Okay. Uh, it is 5 volts, but it's not very stable. I guess I don't really care. It flutters around lower than 5 volts a lot of the time. Big deal. Uh, that'll be fine. So, connect the 5 volt red to the center pin of the MOSFET. Okay. Okay. Connect the right pin of our MOSFET to the motor. Okay. Here's the motor. I wonder if this could even plug into this. It's pretty short. No. I'm gonna use the quick connect to get this stubby red into a proper heck, even this black one ought to go in there actually. Okay. And then we just need a red and a black jumper, male to male. I've been using orange because all the reds are gone. So an orange and a black. Where are you? Oh, here's one. And this, okay. Now, connect the 5 volt red line to the center pin of our MOSFET and connect the right pin of our MOSFET to the motor. Okay, that's going to the motor. Now connect the ground of the Attiny85 to the rightmost pin of the MOSFET. What? Oh, okay, yeah. Uh, Alright, we need another long black wire. This one's got to be really long. Alright. You go to Arduino's ground. Okay. Arduino's ground now goes to the rightmost pin of the MOSFET. Got it. Okay. Now connect pin 3 of the microcontroller to the leftmost pin of the MOSFET. Okay. Let's get a yellow one for that. Currently pin 3 of the Attiny is going to an LED. Okay. Connect the ground of the Attiny to the rightmost pin of the MOSFET. Okay. Wait, the ground of the Attiny. Oh. This should be fine. Okay. $10K ohm resistor time between the left and rightmost pin of the MOSFET. Okay. Connect the ground coming from the MOSFET to the motor. What? Alright, the left pin is the gate, the right pin happens to head back to ground. Okay. The center pin is the drain, the right pin is the source. Source, okay, the drain it goes into from the power supply. Okay. So the far right pin is the source pin that heads off to whatever you're trying to power, in this case the motor, which we have. But what goes to the motor's ground? It's a totally separate line. The motor's ground goes to the ground coming off the 7805 regulator. That's the true 5-volt ground. Okay. There's a buttload of wires going on here, aren't there? Alright guys, here's the motor. He's wired in. Everybody's wired in. There's so many wires! Oh my goodness, this looks really complex, doesn't it? We got wires going over to the motor. We got wires coming way off the printer. Going over my arm. Look at this. These are wires coming from the 24-volt supply of the printer. I mean, we got wires everywhere. This is so sketchy. Okay. Alright guys, I'm gonna do a final pass, making sure everything's wired correctly. Is there a video of the accident that I just had? I imagine someone clipped it. I'd be shocked if nobody clipped that. I just had an explosion. Like 15 minutes ago. We might have another one when I plug this in if something's not right. I want to check my code next. Well, wait, let me just make sure all the wirings are okay. Boom, boom, boom. Okay, we're just pulling ground from the Attiny here. Ground and resistor going across, and then signal coming from the Attiny's pin 3. And that's going to translate. Okay, he'll get the signal. Signal, center one. Comes from 5-volt supply. 5-volt supply goes direct to the motor. Center one goes to the motor, or rightmost one goes to the motor. That goes back to ground of the Attiny. Got it. Okay. That's alright. And then 24 volts comes in. Ground comes in as well. Rightmost pin comes out. Ground also comes out to the motor. Everything's perfect. This is perfect wiring. I just went through it all. Everything. You see all these wires and how much craziness this looks like? Well, I just verified it's all correct. I'm putting the motor in the screen so you can see if it starts turning. I think it will. Alright, let's go over the code again. Okay. Solenoid read-in pin 4. Signal read-in pin 4. Okay, yep. That's good. Pin 3 is pickup roller power assist motor MOSFET PWM pin 3. Yes. Good, okay. While loop is running LED pin 1. Okay, that's fine. Everything looks good there. Debugging is true, okay. Let's comment it out. Pickup roller power assist motor PWM pin 0. What? That's wrong. Pickup roller power assist motor PWM pin 3. Solenoid signal read-in pin 4. Solenoid signal read-in pin 4. It's input. Meanwhile loop is running LED pin 1 output. Okay. Meanwhile, loop is running. LED pin 1. Okay. Just do basic blank is false. Okay. Check 5-volt signal is coming. Solenoid signal read in pin 4. Okay. If it's on, blink the light. Wait. 5-volt signal from solenoid detected. Blink LED pin 1 for 5 seconds. Okay. Blink it for 1 second if it's not on. Okay. Run motor sequence. Okay. Pickup roller power assist motor turn sequence countdown is 1600. Okay, that's the total on time. Pulse off countdown is turn on time. Got it. Okay. Pulse on time. Alright, we switch it on. It's not PWM pin 0 though. PWM pin 3 is switched on. Pin 3 is turned off here. Alright, it all looks good. We just had to update that variable value. So now we're going to plug in the Arduino and upload this latest code. I don't want it to power our Attiny. Do I? Oh, I guess it'd have to. Okay, well. I don't know what's gonna happen then. I guess it's gonna try to. I don't know. Okay, I'm expecting some fire here to blow up. So we've got this pin just flashing on pin 3. Was that expected? Pin 3 used to flash. Now we want pin 3 to be for the motor, and it will only turn on when it's time for the motor to turn on. Pin 1 now is our flashing indicator. So we did change the code quite a bit. Alright, let's go ahead and run the upload. Okay, it's working. You can see a little light flashing now on the Attiny board down in here. You see that little glow coming off it? It's kind of hitting the board. You can see it right here. The board lights up. It's very faint. It's a small LED. You can kind of see it lighting up these little things. And that's flashing, just indicating the main while loop is in fact running. Now, if I move this jumper pin over one or over two, that will short out through this resistor, of course, the 5 volts of the Attiny to pin 4 of the Attiny, which will tell the Attiny it's time to turn the motor. So, and it will turn the motor after a 5-second pause, if everything's working as I think it will. So let's just go ahead and run it. Everything's working so far, it seems. The motor's not turning, but this light's flashing, indicating that's a good thing. But the motor not turning means something's wrong. Alright, ground's getting to the light. When that light turns on, this MOSFET should be turning on, right? IRF 3205. Hmm. Tell you what. Let me move it off that light. Maybe that light draws too much power and it's not able to get enough power to the motor switch, the MOSFET. Alright. Let me try a test. Okay. Uh... That works. The motor comes on. Look at that. Interesting. It's like it wore out the 7805 because there's no capacitor there. Uh, so if you hold it on for too long, it just dies. Oh, it also could have to do with the power supply. Maybe the power supply itself just doesn't want to feed continuously. I don't know. Or it might reach the thermal cutoff of the 7805 regulator. I'm not sure. But, yeah, it just shut off after a while. Maybe it's thermal cutoff. But that's just an observation not related to what we're concerned with. What we're concerned with is our IRF 32 whatever doesn't seem to be working. Our MOSFET itself, RF 3205, 5 volts on. What's going on here? Oh, it's not a high side switch. It's a low side switch. The center pin it needs to get 5 volts into. The rightmost pin needs to go to the ground. No. No, it is a high side switch. It's switching between 5 volts and 5 volts feed. It's a high side switch. Alright, I have another test I can run. Let me get this bad boy out of there, because that was just for testing. So we know the 7805 regulator is putting out 5 volts. We know that that runs the motor. We can see that that pin does go to the center pin of the MOSFET. We know the gate is turning on for the MOSFET because our LED was indicating that pin 3 is sending out juice to the gate of the MOSFET before we moved it off the LED pin, thinking that might be a problem. My gut makes a good workbench. I agree. Okay, so I'm thinking we could run another test where we see if the MOSFET ever switches on. How would that work? I was thinking instead of the motor, if we put the ground here, and the 5 volts output of the MOSFET, we could put right here, and then we could use our resistor to go the resistor's pin goes from ground to one pin of the LED, and then the other pin of the LED goes to... Okay. Okay, the bottommost pin of this LED goes to the resistor, and that's the shorter one. Okay. Got it. And then this goes to the rightmost pin of the LED. Hey, it does light up. It is lighting up. It is lighting up. Barely. Okay, so I don't think it's just sending enough power out of this MOSFET. The MOSFET's just switching on and off so fast. Stop listening. The MOSFET is switching on and off so fast that the motor wasn't turning because it just wasn't enough happening. Everything is working except the timings. The pulse width modulation I'm sending to that motor was just not enough. Apparently he wants he wants full power for longer. So I want that LED to turn on good and long. So let's hop into the code and address that. So, check for 5 volt signal. Solenoid signal read-in pin 4 is red. If it's high, flash the main while loop light for 5 seconds. And that's what it does now, because it's high permanently, because I've got it switched that way. So it's doing that. Run motor power assist sequence. It's coming down into there. Enters the sequence. Full pickup roller power assist motor turn sequence countdown is 1600. Pickup roller power assist motor countdown. Pickup roller power assist motor pulse on time. Alright, that's very low. We have it set up for 1/10 of a second it turns on. That's fine. The pulse off time then, right? Pulse off time is 1/10 of a second as well. I think that's the issue. It's okay to have it pulse on for 1/10 of a second, but once it turns off, it can't be off just as much as it's on, I guess. 5 milliseconds off, 100 milliseconds on. That should work. It's on 95% of the time. We'll try it. Now our light will indicate. This light right here, which is just barely flickering. Yep, it does make a tiny little flicker. If we upload it, it's not so tiny of a flicker now. Or is it? I don't know, it's still kind of tiny. No, it's more noticeable now, right? You guys see it from there now, coming on. Watch this little light right here. See? Boom. You guys see that? Before you couldn't see it at all. I put it on for 200 milliseconds and off for 5. It should be doing that 16 times though. I don't get it. What's wrong here with my code? Run powers this sequence. Full pickup sequence countdown is 1600. Pulse on time is 100. Pulse off a countdown is set to 100. It's switched on. Check if it's time to turn off. If pulse off, countdown is 0. And it switches it off. Pulse off time, which is 5. Switch the motor off. Okay, it switches off. Pin 3. Check if it's time to turn on again. If turn on countdown is 0, pulse off countdown equals pickup roller power assist pulse on time, which is 200. Check if the full sequence is done. Full pickup sequence countdown is 0. Well, I don't know why we're not seeing more flashes. I'm gonna have to turn this thing or set it up to run longer than that then. Maybe my assumption that each one of these are milliseconds. I thought this is 1.6 seconds. Maybe that's not the case. Let's go with, no, it is the case, right? We'll do a 4-second motor turn on total time. Alright, 4 seconds now. Alright, uploading. Didn't change a thing, what the heck? Pin 1 comes on for 5 seconds. I don't get it. There's nothing inefficient about my code, but there is a oversight in it. Something's wrong. It's not inefficient though. Unless if you mean inefficient being too many variables or something, but that's because I created it as a framework that can be built upon for really complex microcontroller code with a lot of simultaneous things happening at the same time. That's why I have the counter system. That way it's non-blocking. If you just put delays in, then if it's trying to turn on and off one motor, it won't be able to control the other 10 motors it is responsible for, not to mention bitbang communicating with a computer through serial communications bitbanging protocols, which I plan to make myself. So it needs to be able to communicate and turn on and off various motors and read various sensors all at the same time, all using advanced counter system and simultaneous tasks with no interrupts. It's all just going to be based on multiple simultaneous threads happening. Okay, check for 5-volt signal coming from voltage divider on solenoid. Yeah, something's wrong here, folks. We gotta find it. I don't think I need this flashlight. It's coding problem. This is working. Laser printer power assist program waiting for motor to power assist pickup roller sequence equals true. Alright guys, I'm just gonna have the pickup roller then, pickup roller power assist motor turn on for 5 seconds. So that'll turn on my light for 5 seconds. Let's see. What the hell? That didn't matter. It's still flashing the same amount of time. Nothing changed. Let me make sure the code's even updating. I might not even be updating the code on the Attiny. Maybe that's the problem. In order to check that, we could set this to go 1 second when it detects it's plugged in, and 5 seconds when it detects it's not plugged in. It's getting the updates. It changed. Well, things are working, but not working properly. Only delays seem to work. My counter system seems to be flawed somehow. What's wrong with my counters? Are these not integers? Int. What about the countdown? That's an int. They're all ints. This is weird, guys. Really weird. Is that it? I think you can't say countdown equals countdown minus 1. Count plus plus semicolon. Okay. That's not cool if this is what's wrong. Like, this is not how I do addition and subtraction. But watch, this is gonna be the problem. Alright, let me run it. Huh. Made no difference. Okay. What the crap then? Now I'm really... Okay. When it's completed, I'll do like a little light show. That way we can talk through all this stuff. We're trying to get some kind of visual display of what's going on, what's going wrong. We'll get some crazy flashy light stuff going on here. Okay. Let me run that. Every time it ends the sequence, it should be like flashing like crazy. Alright, so that's working. Let me show you guys. Okay, one flash, quick flash, then a bunch of little flashes indicating the ending. So the main while loop is running. Pin that's talking to us told us that it is getting to here. So that's good. Oh, What? Where are we going wrong here? You know what? I just realized why the LED is not that bright. This resistor we chose was based upon feeding an LED. Wait, never mind. No, this is 5 volts. That was originally for 5 volts as well. That's weird. I don't know why the LED is so dark. The right resistor. You know what? I think it has to do with not using capacitors along with the 7805 regulator. I think you have to use those. Otherwise you get weird results. Let's Google that though. Do you have wake up capacitors with 7805 regulators? Press return. It can blow up without the input capacitor? I'm using it without an input capacitor right now, so I could get this blown up in my face any minute. Oh my gosh. That's crazy. Well, it hasn't blown up so far, so we're probably fine. There we go. Alright. I'm good without this being here. I think that told us enough. It told us, things should be working. There's nothing wrong with any of our circuitry or whatever. So that's fine. Check if it's time to pulse off. Equals true. Check if it's time to pulse off. This part. This part's sketchy to me. I want to see what it's doing. Okay guys, so I'm going to put a little indicator in. We had the indicator at the end, but I don't really care about that at the moment. So let me just pull it out of there. We want to use this indicator for something else. Clearly we know it's ending before it should be, and it makes no sense, so we're going to put a little checker here to show what's going on at this point in time. Okay. Alright, so it's going to do one of these two things. Oh, it's not a delay of 1. These countdowns would indicate... Holy crap. Okay, so this thing doesn't... This thing doesn't run. Oh, wow, the clock cycles are not 1 millisecond. Holy crap. Because there's no delay in the program at all. These clock cycles could be insanely fast. Oh, it's working, guys! I just figured it out! Oh, wow! Wow. Okay, let me put all the code back to how it was. Our counters in our system are just going based on the assumption that the total program run cycle to run through the main while loop of the microcontroller will take about 1 millisecond to run through the whole while loop, all the if statements. And that's why it seems like it's only turning it on for like 1 millisecond or 10 milliseconds. Because I told it turn on for 1600 cycles, thinking that would be 1600 milliseconds or 1.6 seconds. But because the microcontroller is running thousands and thousands of cycles per second, it's not just running 1,000 cycles per second. It's running like 10,000 cycles per second. So our counter system needs to be multiplied by a large factor to represent more accurately what 1 millisecond actually is. Okay, so nothing in my code was wrong after all. Let me just go back and set all my code back to virgin, because nothing was wrong with my code. This is awesome, guys. This is awesome! We did it! Holy cow, we did it! We figured it out! Oh, what a relief! That was really stressful. When you're looking for bugs, it's like There's no guarantees. I was really running out of hope. Turns out we're good. Alright, boys. So I'm just going to go through my code. I'm just reading through it. Run pickup motor power assist sequence. Okay. Full pickup motor power assist motor turn sequence countdown equals. Okay, I want to set this at the start of the program. We had it at 1600, assuming milliseconds. Should we put a delay? Nah. No, heck no. Heck no! That wouldn't work. Oh. I think I can fix this, guys, without even changing the numbers. We just want the countdowns to update once per millisecond tick. We gotta set up a ticking system. On my computer, I set up my counters based on this. Let me show you guys. Let's see. Aha! Check this out. So in my other coding project, I put initial seconds on PC, if that equals true. So it does this one time. It grabs the system time. System seconds on PC equals my time to W second. Okay. Now, every time it pulses through the program, it gets the local time. Current seconds equals my time to W second. Now, if system seconds is less than current seconds, meaning system time just increased by 1, then it says update timers equals true. Update timers equals true, then we'll update all the countdowns timers, all the counters. So that's the key. Okay, once every 5 seconds it makes them equal again. That's cool. So we need a similar system on our Arduino program, because right now the counters are just going hog wild, and that's a problem. Okay, so that's 1600, that's that, okay. Full pickup motor power assist motor turn sequence countdown equals total pickup roller. Stop listening. Total pickup roller power assist motor turn sequence time. Okay, now we just gotta declare that variable at the top here. Also, these can be put back to 100 each, which was just our guesstimate we made original version. Okay. Alright, so the total turn sequence time is 1600. And so now that's a variable declared at the top that we can mess around with for the total amount of time we want the motor to turn, rather than have to come deep into the code to find where that variable changes, or where it's stated. Okay. So, yeah, that wouldn't damage the LED. They're saying that there's a chance my 7805 regulator might get broken by this, by not having any capacitors in the system. I got scared to put a capacitor in the system since my first one blew up. Literally blew up. Oh, man. Okay. So, where were we? Okay, so I just made that a variable which we declare at the start. Power system motor pulse on time. Okay, that's all fine. Switch on. It switches on. Let's put an enter in. Okay. Check if it's time to pulse off. Check if it's time to pulse off. Okay. If it is time, it'll say true. If it comes to true, turn on countdown equals pulse off time. Well, actually, we want it in seconds. No. We want one clock cycle for our counters to be 1 millisecond. Okay, switch off pickup roller, power assist motor equals true. Switches off. Okay, check if it's time to turn it on yet. Okay, checks it. True or false. Sets it back to pulse on time. Switch it on. Okay. Check if see if the full sequence is done. If it's done, it's done. Okay. 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 Alright, so everything's good. I don't like this minus minus semicolon stuff. It's ridiculous. So we're putting it back to variable equals variable minus 1. Okay. Now, what was that millis talk they had? This one. The author's name is Mellis, and he's writing a program about millis. Weird. Weird coincidence. Okay. Alright, so anytime the button state changes, he sets a counter, he marks the system time, and then he says all the time, system time minus last recorded system time if it's greater than the delay. I think we can work with something like that. Something like that for our counters. Okay. I wonder if I could just copy this directly. Alright, we're going back to programming in my other IDE. Because this is getting kind of extensive. So, okay, let's see. How's it feel to be a master coder? Well, it feels powerful. It's the power that gives me that convinced me I need to create a robot army. Because you can only do so much as a master coder in software. You can make money in software, you can develop programs that do cool stuff and make money, blah blah blah, but to really have that power conveyed in a more obvious way that you can show off, you've got to take it to real life. And to do that, you've got to create robots. Okay. Whoa. That's wrong. Alright, let's get rid of these comments. I'm just fixing all the spacing at the moment. I don't like any comments. Alright, and I don't like open brackets being put on the same line. Okay, good. I used to put comments in my code. That's why those were still there. But I stopped doing that years ago. That was when I first started coding that I created this code, actually. This is old school. It's one of the first things I did with my code. I was still coding baby when I wrote this section of code right here. You're looking at history. You're looking at a time capsule of the past. Okay, so get initial milliseconds on PC. It could be changed to microcontroller. So normally you would use the get local time command in Windows. Okay, but we're going to use the millis command, which gets the milliseconds, I guess. Let me look that up. Returns the number of milliseconds since the Arduino board began running the current program. This number will overflow, go back to 0 after approximately 50 days. 50 days later! That's hilarious. Okay. That's good to know. So, instead of get local time and my time, and then seconds on PC. Okay, first let's just change that to milliseconds. System milliseconds on PC equals millis. Okay, current milliseconds on PC equals millis. If system seconds on PC, let me do one more return. If system system milliseconds on PC equals system milliseconds on PC plus 1. Oh, add 1. Okay. System milliseconds. Okay, if system milliseconds on PC is less than current milliseconds on PC. Alright, so initial time through, it gets it, and it gets it. They'll be the same. But then each subsequent time through, it's just going to get current milliseconds, but this won't increase. So eventually this one will be higher on a pass-through. But not every time, because the system won't always increase millisecond plus 1. It actually runs at higher than 1 millisecond per frame, or per time through the loop. So, yeah, it'll do like 100 passes through here with milliseconds on PC having not changed. Millis will return the same value 100 or 1,000 times or whatever, based on the clock rate. And based on also how much work the processor has to do per run through your loop. So anyways, this won't always be changing, and it will vary how many times it passes through here before this updates. It's only going to update when the milliseconds has gone up by 1. Okay, so eventually it will increase by 1, and then system milliseconds on PC will be less than current milliseconds on PC. Eventually that will happen. And that's the time that we want to update our counters by plus, or reduce 1 from them. Or add 1 to them, depending on if it's a count up counter or count down counter. Okay, so system milliseconds on PC equals system milliseconds on PC plus 1. And that was this one, which was initiated. So that will be plus 1. Program... What the heck? When does program get used? Hold on. I'm wondering what that variable's even there for. Alright, we don't actually use that variable ever in my code. So I'm going to get rid of it. Okay. And we definitely won't need it today either. So get rid of that. Okay. System milliseconds is less than current milliseconds. System milliseconds equals system milliseconds plus 1. Update timers equals true. If current milliseconds on PC equals 0 or 5 or 10, make them the same. No. Alright, so it's going to start out the program at the very beginning. It will pull the milliseconds of the program, which will be 0, I guess. And so will this, because they're going to happen right after each other, so they'll both be 0. But then as the program continues and continues, it only did this the one time, so this one will never change. Eventually this one will go up to 1 millisecond the program has been running for. And at that time, system milliseconds and current milliseconds will no longer be equal. So system milliseconds, if it does not equal, then it will make them equal, but it will also know that the program just went through a full millisecond. So then it will update timers. At that time, the timers will all increase or decrease. In this case, they all are decreasing by 1. But that will only tick through once every time we detect the program has run an extra millisecond. Now, in the event that system milliseconds is 1,500,000 and current milliseconds drops back down to 0 when it overflows, this will become 0. They'll no longer be equal, so it'll just get set back. They'll both be 0 again. So this solves even those overflow circumstances, and everything should work perfectly now. I also want to update my old code to reflect this better way of handling things. This was my old school code here. So if initial seconds on PC equals true, this is before I became a long variable user and stopped using comments instead. Instead, I just began using long variables for everything. Alright, so initial seconds on PC equals true, equals false, get local time, seconds on PC equals my time to W second, get local time, seconds on PC equals my time to W second. If system seconds on PC does not equal current seconds on PC, then system seconds equals. Eventually it will not equal system seconds on PC because that never updates after that. So eventually this will go up by 1, and at that time they won't be equal, they'll be set to equal, it will update the timers. And that will just keep happening every time this goes, every time this changes in whatever way, that will trigger an event. So this is no longer needed, this corrective code. So that will work great. Put an enter there, and put a space there. Okay. So I just updated some of my code for my other program. Oh, and by the way, okay, so this corrected our timers problem. Now our timers should run according to what we expect, which is once every millisecond they'll update. We just made that wild assumption. The program doesn't run at 1 millisecond per cycle. It runs at countless milliseconds per cycle. So our countdowns were going da 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 da, so everything seemed instant, and the lights or motors never even had a chance to turn on because everything happened so fast. So this should solve all of that. So we can now paste this back into Arduino. The only problem is we didn't declare any of those variables. So we need to do that. Okay, update timers was new. System milliseconds on PC is new. I'm just going to paste all the new variables that are not declared in Arduino into a notepad file, and we'll declare them all together at the end. System milliseconds on PC, we have that. This one also. It needs to be initiated to true. Okay. Alright. Alright, I'm running the update. I think it's working! Yes, it's working. 8 times it's flashing. Alright, so we had it set up to be 100 milliseconds on, 100 milliseconds off. So it should have equally timed flashes, which it is. And then it does it 8 times because we did 1600 total milliseconds that we want it to be able to even run this. Now it's barely even turning on, and the reason for that is our 7805 regulator is pissed. Why is it pissed? Because it's supposed to have a capacitor on its input. Okay, so we need to note that down. We really need to put a capacitor on it. Let's see. I fixed it, guys. It was a timing thing. All of my timers were based on milliseconds in the program, and I assumed that one pass through the while loop of an Arduino would take 1 millisecond. So I figured that would be about a good estimate. And I totally forgot that assumption. And so when I ran my program, all the counters were counting down to 0 like instantly. And it's because the Arduino ran a lot faster than one passage through the while loop per millisecond. It ran like 1,000 passages through the while loop per millisecond. So all my counters counted down to 0 instantly. And so I thought there was some kind of logic error or gating error, but it was actually just doing its job. I just didn't have the counter set high enough. So rather than make the counters arbitrarily set higher until they started matching the time duration I expected, I instead made the counters only update on an event, and that event being each time the millis function returns a greater value than its last return. In other words, each time milliseconds of the program incremented by 1, then count down one off all the counters. So there has to be a trigger based on the event that the millisecond count went millisecond count plus 1 on the Arduino. And thankfully it has that command where you type in millis, open parentheses, close parentheses, semicolon, and that returns a value that eventually will increase based on some counter system built into the Arduino. Or not even the Arduino, I mean in this case it's not even an Arduino. In this case it's a Attiny85, but every microcontroller that works with the Arduino IDE will have that capability of keeping count of the milliseconds since it started running. Once every 50 days millis resets to 0, but that wouldn't matter because anytime millis just changes value to something new, my program triggers an event to have all the counters update. So that solved it. Wake up. Okay, here. Stop listening. Alright, so you're supposed to have a 10 UF capacitor. It could be 0.33 UF. is recommended by datasheet for here, but 10UF is most often recommended by people on forums and stuff. 25UF or even up to 100UF should be fine if that is all you can find lying around. This capacitor is not even needed if the 5-volt regulator is near to the power supply filters. But if there is a substantial wire distance, in our case there is, then this capacitor is needed due to the inductance and long lengths of wire causing delays in power being sent during demand spikes. Alright, we're going to have power coming into the left pin and the center pin. Oh, we still have that set up. Okay. We want a 10UF capacitor between power and ground with its striped side toward ground. Okay. Let's get out another 10UF capacitor. Well, no, I'll just write it down for today. Add a 10UF electrolytic capacitor rated for a minimum of 25 volts with its striped side connected to the center pin of the 7805 regulator and its other side connected to the leftmost pin of the 7805 regulator. Alright, I'm actually going to do that now, I think. Sitting up has made my shoulder feel better. So now I feel like I can kind of work a little bit again. But not too much longer. I am about out of time. There's something else. 100 ms ceramic capacitor is recommended by many for the rightmost capacitor, but 10UF electrolytic is recommended by some great tutorials and the Arduino website itself. I have confirmed 100% that 10UF is used on a very popular tutorial on the main Arduino site that has been verified by many. So I'm keeping it as 10UF here in my diagram and a link. However, in my first circuit I'm going to use a 100 NF ceramic since I have it on hand. I can't believe we're figuring all this stuff out, guys. This is awesome, man. We're making real headway here. It'd be pretty cool to figure out what happened to that one capacitor that blew up earlier. Here's a 10UF 50 volt capacitor. They look like they're all 10UF 50 volt capacitors. What the frick? I don't get it. Why'd we get an explosion then? I need solder wick. I gotta get all the solder off the legs of this electrolytic capacitor here. Let's put some flux on it. No, we gotta put it on here. Look at us getting out all our tools now. Goodness. This is supposed to be just a quick thing. Getting out everything. What the heck? Hey, I got an idea. Alright, I put in the electrolytic capacitor here by the 7805 regulator now. There it is. It's spanning between the left pin and the rightmost pin. That should make the output more dependable, because the output was total crap before. And then, yeah, you're always supposed to have that. Somebody said your 7805 regulator can blow up if it doesn't have that, and I've been using it without it. So I was taking a risk there. Alright, so now spanning the center and right pin, we've got a ceramic capacitor. We just got it wedged down in. Let's see if you can see it. There. You can see it right here. That little brown thing. What the heck? There, I'm touching it. Right there. So now that's spanning between the center pin and right pin. And that's the same as we have here in our notes. The left pin and center pin has to be spanned by a 10 UF, and the right and center pin gets to be spanned by a 0.1 UF or 100 NF ceramic. But you could also use a 10 UF electrolytic as well. So with those added in, things should be a lot cleaner. I kind of want to try it now. I think we should try it. Heck with it. I want to try running the motor like that. Yeah, we'll run the motor to test it. Because before, the motor would just turn on for a little while and then shut down. And we thought it was some kind of thermal shutoff, but no, it was a malfunctioning of the 7805. Oh shit! It almost blew up again. What am I doing wrong? Oh. I put the stripe side again toward the wrong side. Oh my gosh! Why do I keep doing this to myself? It started smoking. It was about to blow up again. Gosh, why did I do that? And nobody even called it out. The stripe side has to go toward black. Thank goodness it didn't blow up this time. It was about to, though. Pulling out my 7805 regulator. I don't know if I trust... Nah, I don't trust that capacitor anymore. Black stripe goes toward... Or do I? Should I trust it? I mean, it just started burning, right? We caught it in time. I saw the smoke starting. That's got to be a common problem, right? Putting in electrolytic capacitors backwards? It's got to be. It looks like it's holding up. It started smoking. I guess we caught it in time. Alright, so our 5-volt output should work now. Let's see. That goes to here. We would need... We need some wire. Some jumper wire. Alright, this one will work. I think this is the same wire we used last time, actually. Okay. So we need to put this one right here. We need another one for ground. This will work, okay. Get this thing in my way. Okay. So this now is connected to the ground of the 7805 and the 5-volt output of the 7805 through this being connected on the same rail as the rightmost pin. So these two have a 5-volt potential between them, and I can verify that with a multimeter, which I don't mind doing. I would like to do it. Okay. Yeah, it's 5 volts, okay. So let's toss that into... Hold on, let me put the probes away. Put my multimeter away. Okay, get out my motor. Okay. Alright, this should run the motor. I guess... Oh, wow, it's hot as hell! Whoa! No wonder it cuts off! The motor overheats the crap out of the 7805 regulator. That regulator is set to be able to output 5 volts coming down from 24 volts at 1 amp. I figured this motor probably only will pull like half an amp, but maybe the 7805 regulator just doesn't have a heat sink on it, and it's just getting hot. I touched it, it was hot, so that's why it shuts off. Well, fortunately for us, it won't be for continuous rotation, because we're just going to be turning on this motor at pulse width modulation, and only for 1.3 seconds or whatever, not for like a long time like we were just trying to do. So we should be fine, but putting a heatsink on it wouldn't be a horrible idea as far as like the longevity of it, or using a pair of 7805 regulator to split the work between two, although that'd be a bit of a pain in the butt. But yeah, that didn't really prove anything except we now, I don't know, maybe it proved something. No, it proved how hot it gets, and it's a thermal cutoff, which is why the motor shut off earlier. That's why it's shutting off now. It's a thermal protection, which is pretty cool. I'm glad it protects itself rather than burning out. I don't want to see more magic smoke coming out of my stuff. I already had one explosion today and saw smoke another time today. I mean, I'm pushing my luck here. I'm going to lose an eye. We can't be having our electronics exploding all the time. Close window. Stop listening. It's not fun to have the electronics explode. Gotta dot my I's and cross my T's here. But we're learning, man. We're learning tons, and we're improving. Everything's getting better. We are getting it, guys. We are just killing it. What a productive session. What a excellent day. What a productive and excellent day. Wow. I'm a superhero. World's greatest roboticist proved it once again today. Without a doubt. Unstoppable. Get wrecked. Man, we're on fire here. We are on fire. Who'd have known electronics would be so darn easy? Well, everything's easy when you're a genius. I guess I should have expected it. No challenge at all. It's a joke. Electronics are a joke. Electrical engineering degrees, what a joke. I learned the entire field of electrical engineering just putzing around on YouTube and Wikipedia for a few days. Okay. Gotta tell you, man. Add 10 UF electrolytic capacitor rated for minimum of 25 volts with its stripe side connected to the center pin, which we screwed up. And its other side connected to the leftmost pin of the 7805 regulator. Did it. Did it. Okay, so the next session that we come back in here, we're going to be experimenting visually with getting pickup roller to turn on the laser printer and match the rotational speed with pulse width modulation of the DC motor so that we can get a speed match approximately and ensure the motor turns counterclockwise as we will mount it facing to our right. So we're going to be messing about with getting pulse width modulated motor speed control to fairly match the speed we need the motor to be turning. So we're going to be playing with getting motor speed customized with our code next. We were supposed to do that today, I thought, but we ended up doing all kinds of other stuff and getting slowed down by all that other stuff, which is fine. We learned something really important about timing, and that's very related to this, getting the motor's timing right. I mean, technically we did work on motor timing. Anyways, huge win. Alright guys, so I'm probably going to watch James Bruton and make dinner now. I'm watching his entire YouTube channel, first video onward. He's a roboticist like me. He also does cosplay. I don't do cosplay, but I do robotics. And all of his cosplay involves some robotics. He does Iron Man cosplay, and he gets his Iron Man suit to light up and do things based on microcontrollers and stuff. So it's really educational for a new roboticist to watch his videos, and then he actually gets into hardcore robotics as well. So anyways, I'm going to do that, and I'm going to eat, and our next electronics session on the laser printer, we're going to be able to get that motor turning at a precision speed using pulse width modulation, or just using on-off at the correct amount on milliseconds, correct amount off milliseconds, and we can control the speed that way. And once we've got the speed ironed down, we should be good to go. You know what? Part of me feels like I shouldn't even be using a 7805 regulator to power a motor now. Let me Google that. That'd be a fun thing to Google. Wake up. Can I use a 7805 regulator to power a motor? That's probably a very common question. Stop listening. It's a very common question. I knew it would be. Oh gosh. Mine's 24 volts minus 5 volts, 19 volts times 1, 19 watts. It needs to 19 watts of heat. $60 is a light bulb. It's getting, that's, whew. $19 times 20, $190 times 2. 400 C? I'm gonna need a switch mode power supply buck converter, because that's just too much heat to be trying to dissipate. I have one in here, I think. I think the 7805 regulator, well, I mean, it could work. It's not continuous, and it's only for a brief minute. Yeah, you know what? Nah, I'll use the 7805, but we got to make sure it's pulsing, and I mean, it's going to happen quick, though. Oof. I mean, we'll need a heat sink. Oh my gosh. Maybe we should just go with switch mode power supply. Well, let me read more. Buck regulator. Yeah, they're saying use a buck regulator anytime you power a motor, solenoid, or relay. Might as well go with best practice, right guys? Where is our buck regulator? I'm sure we bought that. Oh my gosh. Where is it? I'm trying to find a buck regulator in here. I'm sure we bought some. I got a GPS module in here. I don't even remember all this stuff I'd be buying. Radio transceiver modules. Okay, that's cool. Wi-Fi modules. Buck converter! Input 4.75 to 23 volts. Output 1.4 to 17 volts. Oh, come on! It goes up to 23? Oh, hell no. What the crap, man? I equals V divided by R. I don't believe this. Oh, I know how to drop the voltage down. If you put it through a PC cooling fan, doesn't that drop the voltage? Hi, Death Panther. Hi, Liz. Huh. I don't know what to do. This only takes 4.75 to 23 volts. Whoa! Are these really that small? Holy crap. 1.8 amps. That's perfect, though. Oh, it's so small. I'm taking this thing out. I knew that. What would you do if you banned somebody and they create a new account 2 minutes later and do what they got banned for? Would you not do the same? Just make a 1 week follower only mode so that somebody can't harass you with unlimited fake accounts and just break the same rule over and over? I think you would do the same. Yeah, every time that happens with someone, I put it on 1 week follower only mode for about a year. And I hope that that person is gone by then. Then I lift it. One bad apple spoils the experience for everyone for a whole year. I got hosted for 500 viewers the other day and nobody could talk. Probably could have got a lot more followers, but somebody had to ruin it for everyone. forgot your question. Can I use a buck converter? Wake up. Wake up. Can I use a buck converter with a maximum input of 23 volts and input 24 volts? I think I have the same lifestyle philosophy as people living on a space station. They have everything they need for life support in a small area. Stop listening. And I do the same. Because I don't like having to walk around the house to get things I want. I prefer just to stay seated most of the time. It's more efficient. Just do a voltage divider? Wait. Stop listening. Stop listening. No, I don't think you can do that. Not when you're running a lot of current. Voltage dividers are really for just taking readings, like measurements, at very low amperages. But you're not supposed to do it when you're talking about like running a motor. That would just make the resistors have to be really high rated. The big white ones, and that's very unprofessional, and they'll get red hot. They're like huge ceramic resistors. I prefer just use normal quarter watt resistors for everything. I don't even have giant resistors of multiple different resistance ranges. That's just not something that's an option. But that was good thinking, though. I want to try to see if on eBay they just made that number up when I bought it. It might go up. It should go up to 24 volts. Why would a stupid buck converter stop at 23 volts? Like 24 volts is 2 lead acid batteries. 24 volts is a lot of things. It should for sure handle up to 24 volts. 24 volts is a very standard number in electronics. Why would it stop at 23? That's ridiculous. They can't do this to me. I have rights. MH Mini 360. Guys, look! Stop listening. Alright. This is the buck converter we own. It's called a Mini 360 DC-DC buck converter. It has 4.75 to 23 volt as its input. Now, I noticed while I was looking at it that it had the MP2307DN buck regulator IC. MP2307, I looked up the data sheet for it. It's a buck converter chip. It requires a resistor, a couple capacitors, capacitor, resistor, an inductor, and a capacitor. And it's just this little chip with a little bit of supporting circuitry. It has an input, has an output. And anyways, I came down to here and it says absolute maximum ratings. Supply voltage VN can actually be up to 26 volts, not 23 volts. Switch voltage -1 volts to VIN plus 0.3 volts. Boost voltage -0.3 to 6. All other pins junction temperature, lead temperature, storage temperature, recommended operating, input of 4.75 to 23, output of 0.9 to 20. This says going up to 17 volt output. So that proves that those are just like conservative. Let's see, exceeding these ratings may damage, but if you don't exceed it, you're okay. Absolute maximum ratings. Recommended versus absolute max. Wake up. Recommended. Wake up. Recommended versus absolute maximum ratings. Guys, I feel good using this thing, because we're only going to use it for like 1 second at the maximum rating, at well under its maximum amperage output. Stop listening. So I don't think it will harm it. It's only recommended to use up to 23 volts. We're only using 24 volts, only one little volt, and we're not going to have it running 24/7 like that. It's just to turn on a motor for a brief moment. Put away 7805 regulator and capacitors I have with it. Put in our buck converter in place of the 7805 regulator on our breadboard circuit. Alright, I feel good with... Stop listening. I feel good with it. So we're going to use that buck converter, even though it's 1 volt over the recommended input, but it is within the maximum rating input. And it said 26 volts. So I'm going to make a little note of that also on our sheet. Man, that's a little baby-sized buck converter. How funny. It's even smaller than my dip package 7805 regulator. Grief. Okay. Alright, so we're gonna switch to using that buck converter instead. And everything else looks good. We can still do all the testing we have for now as is. Well, no, we want to use the buck converter right away. So we'll switch to the buck converter, then we'll do all of our tests, which is what my to-do list says to do. Then we're going to get the motor to turn at the appropriate speed. And now with that buck converter, we're dealing with higher efficiency, and we're dealing with no longer reaching the thermal cutoff of the 7805 regulator, which is having to dissipate an insane amount of watts in the form of heat. It's ridiculous. It's not efficient at all, so it's just forming so much heat I would need a big old heat sink. That's ridiculous. So buck converter, you don't need heat sink. So that will solve it once and for all, and that will power our motor. And yeah, that should do it.